Buongiorno. So, in this stream, we're trying to get, like, a few streams ago, I wanted to get an autoencoder because we wanted to understand on a conceptual level, like, how an autoencoder works, and, like, the autoencoder, like, these are the input images, and these are the outputs from the autoencoder. And so it doesn't work. And it's also not really... Oh, yeah, I just realized... I was going to say it's not really an autoencoder because... No, yeah, that's correct. It's not even an autoencoder because, like, the concept of an autoencoder is the hidden layer or the latent code is smaller. Like, you have less numbers than the input images. And in our autoencoder, it's the same number of, right, like our images are 8 by 8, 64. And so the latent code is 64. So, like, there's literally no compression happening, and it doesn't work. So, because, like, our original motivation, we were just like, yeah, if you haven't, like, how does an autoencoder work? Like, how is it factorizing the weights in the... like, somehow it's storing elements of the data in the weights. And we're gonna try to look at that. But, yeah, we couldn't get it to work. So, like, it doesn't train. And we tried regularizing the weights here, and that didn't really seem to do anything. So I think I'll take that out, and then like, lowering the training step. And okay, so, like, that's a little better. So what's going to happen now is, like, at some point it's going to stop training. And see, like, right now it's training because when a new batch comes in, okay, so now it stopped training. So yeah, like, this like, these are the outputs. So like, it's kind of correct, but it's very noisy. And also, the encoder and decoder weights are completely non-interpretable. So I think I'm just gonna try to make the input image dimension smaller yet, and because like, yeah, like, it should be interpretable, and also there shouldn't be as much noise over here. This may be a like, an impossible task. Also, let's see, I was yeah. Alright, so yeah, I think I'm just gonna do that. I'm going to make the image size smaller to hopefully make things more interpretable. I'm in. Alright, so we'll go, like, 5. And yeah. And this needs to be... I guess that doesn't matter as much, but image size, so we can say up to 4. Alright, is that gonna magically work? Oh, it kind of did. Kind of. What's with the decoder weights? Why are these decoder weights black? We gotta figure out why those are black. I mean... decoder weights... Oh... this should be... image size? Or... So the latent code is the same size as the image. So it should just be straightforward to learn. And encoder weights is, yeah, just image size by image size. Just 25. And this is 25. And I think this should be 25. And this should be 25. I don't know if I'm doing this correctly, frankly. Yeah, that looks good. So I mean, it's kind of working, but yeah, I mean, I guess it works. Like, I mean, it's noisy, but right, I mean, like, the images match up pretty well. Kind of. Yeah. It just happens to be completely non-interpretable. Now, also, I was using linear activations. So, does it also work if you don't use linear activations? Yeah, I mean, it seems to work. It's just completely not interpretable. I wonder. I mean, it's just kind of the problem. I mean, it's like, okay, so like any one of these images in the outputs is explicitly a linear combination of the decoder weight images. And so I think like we're hitting the problem of we're kind of hitting the problem that like linear combinations of weights are like impossible to, or like linear combinations of images are like impossible to interpret. What if we let the squares be size 1? And, do this. See, if we go back to, I mean, like, okay, so, like, if all the activations are linear, then if all the activations are linear, then you're just doing like a matrix. Yeah, I mean, you're just doing a matrix. You're doing an arbitrary matrix multiply, and then like the transpose of the matrix is all like, yeah, any set of weights such that, I mean, maybe that's, yeah, we could do that actually. We could take these weights as vectors and then add, well, yeah, and then just multiply the encoder weights and the decoder weights. And they should be like the identity function or the identity matrix. And then, yeah, I mean, I guess that's basically the level of interpretability you can achieve, because, I mean, the solution, if everything is linear, then literally the only requirement is that, like, the first matrix is full rank, I think, and then the decoder matrix is the transpose of the first matrix. So, of course, I mean, like, when you add multiple layers, then it's not really clear how to interpret anything. But yeah, I think we'll do that. We'll check if the two matrices, when you multiply them, if they give you the identity matrix. And so, like, in terms of layout, I think I'm out of columns. So, I mean, like, where's it gonna put it? Okay, so we have to play around with CSS very quickly, because I want it to go under everything. Yeah. So, oh no. Yeah, like, I put it in a new column. Yeah, I don't know how to specify, like, I don't want it to be in a column, or like I want it to be under. Okay, so I think this is flexbox, like, new row. I need a new row. Or just, how do you use Flexbox? Yeah, just give me an example. Class, row reverse, multi-line, flex wrap, display, row wrap, flex shrink. Yeah. Okay, what if I just say flex wrap? Flex wrap. What does that do? Yeah. That is not what I wanted it to do. Well, let's just try all the options. What are the other options? Wrap. Inherit. No wrap. Alright. Flex flow row wrap. No. What about column wrap? No. Okay, so there's no easy way of doing this, so that's fine. Okay, so we'll just make the matrix thingy. So like we're gonna check that the encoder weights multiplied by the decoder weights give the identity matrix, which I'm pretty sure they will. Actually, I mean, it'll give like a noisy version of the identity matrix. And yep. All right, so we need to add a canvas for this matrix. It's kind of like you could just insert these divs programmatically, but we do it mixed. So let canvas document create element of type canvas, and it's going to be so we're interpreting the images as one-dimensional vectors. So it's, like times image size times image size, and then matrix div append child canvas. I just realized that needs to be like that. Okay, and then to draw the matrix, we need the weights. So it's just the, I don't think it matters what order. So it's like these. This probably isn't going to work easily. So it's the layer 1 weights. These are the encoder weights. This isn't going to work easy because of that index. Map mul, I think, that's cool. And so matrix multiply with the decoder weights. Oops. Okay, let's see what that does. Probably breaks, but you never know. It's not a function. I thought it was. Matrix how do you multiply? Do I have to do einsum? Yeah, I don't want to do einsum, dude. I just want to multiply two matrices. Basic math. Mat mul. You have to capitalize. Capitalize. Okay. Now what do we got? Yeah, what's its shape? I'm surprised that worked. 25 by 25. That's exactly what it should be. Huh. Well, it was just that easy. And so then we do a little array sync. And then we'll just draw it. We will just draw it. Yeah. Okay, canvas is the matrix canvas. What did I call it? Yeah, the matrix canvas. And image size and matrix RC. And that should totally work. Alright. Whoa. Yeah, but that's not, oh. Yeah, it's because it's the square. Okay. Whoa. Yeah, it is. It's learning. It's learning a noisy version of the identity matrix. So that's... Oh yeah, and also, are we using linear activations or... Okay, so what if... It should work both ways, but... Just for... Yeah, so... It learned... a noisy identity matrix. So, I mean, basically, what that is saying is that you cannot interpret really what this neural net is doing, because all it has to do is, this first transform is just any arbitrary matrix, and then the second transform is just the transpose of that matrix. And, you know, I mean, the matrices can be completely... I mean, the first matrix is completely unconstrained. It can be like any matrix. It just has to have a transpose. Or I guess like an inverse. Which, you know, it has to be like full rank or something. Now, I mean, it's not like it's not a perfect identity matrix, so I don't know what the deal with that is. Like, in particular, it has these little... Also, like, these should all be zeros, meaning like they should be black, I think. Unless my color map is wrong, which is probable. Oh, what if I... Yeah, where's my color map? +1 divided by 2. Yeah, let's not do that. Much better. Yeah, so I mean, like, it's just learning a noisy identity matrix, and yeah, I mean, it's just not interpretable by humans, because I mean, it's literally saying, like, you know, like, this output image is the linear combination of all of these images weighted by the activations in this image. So I mean, like, it works mathematically, but like it's, you know, like you're not going to be able to interpret it. Also, I don't know why it's like a noisy version. Like, you'd think it could like learn like a non-noisy version. Yeah, I mean, that's also kind of the thing, which is like in an autoencoder, like if you have an actual compressive latent code, then it's kind of like, I don't know, you have like a weird thing where it's like the weights when multiplied have to be the identity matrix like on the data, but not the identity matrix not on the data. Let's go back to linear activation. I mean, like it works better with linear, which I guess would make sense. Isn't that a so like if you have the concept of if you have the concept of a matrix that is the identity function on like a subspace of the data, isn't that like eigenvectors? So is that what it's saying? Like, so like if you had a compression, if the latent code, let me So I think we're saying like, yeah, if you're just treating this as, so this you can interpret as like a matrix multiply, and then you need a matrix over here that is the inverse of the matrix, of the first matrix, except it doesn't need to be the inverse on all of the data. It only needs to be the inverse on some of the data. So yeah, isn't that eigenvectors somehow? It's like you need to find, like, if you're going to do a compression, like, it'll be possible if all the data, like, if the inputs are coming from a linear subspace, and you can find, so basically the eigenvectors of that linear subspace need to be, or like the eigenvectors of this matrix need to span the linear subspace that the data are coming from, in order for the compression to work, I think. Yeah, I think that makes sense. It's kind of problematic though, because I mean, it's not clear that like image data come from any linear subspace. But I mean, you know, you could just like, you could have like a general statement. If I'm generating data from some low-dimensional linear subspace, then my autoencoder will work in as much as like gradient descent can find matrices like whose, like the encoder matrix, the eigen vectors span the linear subspace of the data. Yeah. And it's also like, what if you have multiple layers and the but I think that, I mean, I think that that's like a general, this might be a thing, like an autoencoder will work if data are from a, you know, linear subspace and the encoder matrix well, I mean, like, well, yeah, it's from a linear subspace of dimension, you know, d, And the encoder matrix, I think it's like the eigenvectors of the encoder matrix have to span, although it's like, I mean, you know, you're not going to have eigenvectors because it's not a square matrix. But the pseudo eigenvector, I don't know. I'll just put a tilde of the encoder matrix, and the eigenvectors of the span the subspace. What? I think that makes sense. Because I mean, like the encoder, like basically you need the encoder matrix times the decoder matrix have to equal the identity matrix, like on the linear subspace only. Right? Is that like a thing? Can you have a concept of an identity matrix only on a particular subspace, but not like other subspaces? So yeah, we might look at that later. Alright, thanks for watching.